bring into, because an application for exponential that is very commonly used. If the number of occurrences of an event or change during a specified period follows a Poisson distribution, then the waiting time until an event occurs and the time interval between successive events will have an exponential distribution. And a lot of people, what they'll say, the big focus you'll hear on this one with the exponential is the waiting time until a first event occurs. And that follows an exponential distribution. So again, the number of occurrences of an event or change during a specified period follows a Poisson distribution, then the waiting time until the first event occurs, and the time interval between successive events will follow an exponential. So you have, think about it like you have two different random variables. The number of occurrences, y, the random variable y, it's a discrete random variable, follows a Poisson distribution, which we know would have a mean or an average. Mu is equal to lambda, whatever rate is given to you. We know from previous discussions that probability y is equal to some number, and that should be actually a capital Y, is equal to some number k, is equal to e to the minus lambda, lambda to the k, divided by k factorial. This is all from when we were looking at the Poisson distribution in the discrete distribution random variable sections. And that's how we define Poisson distributions. Now the wait time until the first occurrence x, a different random variable, a continuous random variable x, will follow the exponential distribution with theta is equal to 1 over lambda. And it's kind of the wait time until your first occurrence. And that is then the probability distribution function associated with this random variable x is just as you say, just as you see, it can be simplified. Now we looked in the previous slides that, well, an exponential distribution with theta will be 1 over theta times e to the minus x over theta. But now if we replace and say theta is equal to 1 over lambda, then p of x for the random variable x becomes becomes lambda times e to the lambda, negative lambda x. And you can use lambda then, both in the Poisson, but you see this close relationship. I always think of it intuitively as, okay, suppose you are told that cars arrive at a repair station 2 cars every hour. Well, what's the wait time until the expected wait time until the first car appears in the next hour? That's going to be 1 over 2, or 1/2. 1/2 of an hour is 30 minutes, right? So it's intuitive. If I tell you 2 cars are coming in, that's the average arrival time rate, 2 cars per hour, then the wait time until the first car coming in would be 30 minutes. So that's kind of, intuitively it makes sense that these two are related. The number of cars arriving or the number of events happening, Poisson distribution. And how does that relate to another random variable that tracks the wait time? And again, time, you get into 30.1111 minutes or 30.2 minutes or 30. It's a continuous. Time is continuous versus the number of occurrences, the number of events happening being a discrete one. So, but of course, in this case, they're related. And the Poisson and the exponential give you the two specific distributions that'll be followed. If you assume that the arrival follows a Poisson distribution with a particular rate of lambda, then the wait time will be related to that, and it will follow an exponential distribution. Okay, so cars arrive at a gas station randomly every 2 minutes on average. Determine the probability that the inner arrival time of cars does not exceed 1 minute. So lambda is equal to 1/2 arrival per minute, half of the car, so to speak, or per minute. And therefore, we're just going to be plugging in to find that what's the probability of the time between until the first car is another way you could look at that, is less than a minute. Well, that's going to be 1 minus e to the minus lambda times 1. 1 minute is our measure. And that's going to be 1 minus e to the minus 1/2 times 1, or 0.3934. Let's see. The breakdowns of industrial robots follow a Poisson distribution with an average of 1/2 of a breakdown per 8 hours, per 8-hour workday. If this robot is placed in service at the beginning of the day, find the probability that it will not break down during the day. It will work for at least 4 hours without breaking down. So give that one a shot. Okay. One last thing about the exponential distribution, it has this property called, it has a forgetfulness or a no memory property. That is to say that the conditional probability that x is greater than or equal to t plus h, given that t has already gone by, is just equal to the probability that x is greater than or equal to h. So what's a way to look at this? This is it's an interesting property. So the probability that you'll be waiting at a bus stop for 30 minutes, given 10 minutes has gone by, that is the same as the probability of waiting 20 minutes more. It doesn't matter. So did you hear what I just did? So probability that you wait 30 minutes, given that you've already waited 10 minutes, is the probability that you're going to wait 20 minutes. Probability that you're going to wait 380 minutes, given that you've already waited 360. 360, that's 6 hours. Whew, that's a long wait for a bus. Probability that you're going to wait for 380 minutes, given you've already waited for 360, is also equal to the probability that you wait 20 minutes. So it doesn't matter whether you're doing, how much time has gone by in either of those cases. So that's a pretty extreme example. Let's see, put another way. Regardless of the length of time that is elapsed without an event occurrence, the probability that an event will occur in the next h units, in this case minutes, always stays the same. You've waited 6 hours or you've waited 10 minutes. Either of those other examples I just gave, you have the probability that you're going to wait 20 more minutes. It's the same. Okay. What additional kind of extension or where do people go with this? And I bring this up because the exponential, that relationship between the Poisson distribution and the exponential, there's this other distribution called the Erlang. Exponential random variable, this comes up quite a bit in queuing models, and in terms of, and we're not going to cover that particular application, that application too much, but the idea of you go to Disney World, and you are, let's say you're somebody who works for Disney and you're trying to figure out the line configuration. You're trying to figure out the staffing of the number of workers to have on staff during certain hours of the day. Well, of course, all that's going to be related to the expected number of customers coming to a ride, let's say. And so how do you set that up? And so you're going to be interested in knowing the expected wait times of people in line for a ride at Disney World. Well, so the exponential distribution, and that's what a queuing model gets into. That's what queuing theory and software applications get into. You could also look at queuing models going into factory configuration, and you have a particular bottleneck machine, and parts are being made, multi-stage manufacturing process, and you may look at the queuing associated with parts coming to this particular machine, and the impact of buying more machines or configuring your factory layout different ways. A lot of times people will run queuing models, queuing software. Okay, so exponential random variable describes the weight or the length until the first occurrence or event in a Poisson process and is given by the parameter theta. A generalization of exponential is the wait time between R events or occurrences. The Erlang distribution is given by non-negative integer shaped parameter alpha and the rate lambda, which is a non-negative real number. When alpha is equal to 1, this simplifies to an exponential distribution. So, the exponential distribution, people kind of say, well, if you go back to what we were doing in the discrete random variables, what did the geometric distribution give us? Put your hat back to the discrete stuff. And we were interested with the geometric, how many times do you repeat until you get your first success, right? In a sense, exponential is similar feeling, right? What's the wait time until your first occurrence on the continuous? So I've kind of just jumped between those two. But you're in the geometric and in the exponential, you're interested in the first time you have a success, the first time or the next time you have an occurrence. Generalization of exponential is the wait time between R events, okay, or occurrences in a Poisson process. Erlang distribution, so it's a different kind of question that's being asked and worked with an Erlang. But that, just to give you an intuitive, so if you actually go and use queuing software, you'll see exponential and you'll see the Erlang associated with the different times. Okay, I'm going to cut off at this point, and we will return on the next recording session with gamma distribution.